Hello, everyone. My name is Andy Benson, and the paper that I am presenting on is Designing New Operating Primitives to Improve Fuzzing Performance. And this paper tackles the problem of how to improve fuzzing by improving the speed of execution of new test cases. This paper was originally published in 2017 by ACM. So before getting started with the paper, I just wanted to first introduce the authors and their backgrounds to give a better understanding of who made this paper. So going through the authors, Wen Zhu has a PhD in computer science from Georgia Tech, which he earned in July of 2023. So this paper was published during his PhD. And he currently is a co-founder of Narya.ai, which creates AI productivity nodes. And this is pretty different from fuzzing and the concepts of this paper, but his research also focuses on automation of bug finding with his company. And the next author, Senadaya Kashyap, was also a PhD student at Georgia Tech at the time of publication, and he currently serves as an assistant professor of computer science at the École Polytechnique Fédérale de Lausanne in Switzerland. And his past research has focused on operating systems, concurrency, and distributed systems. And Changwoo Min was formerly a professor at Virginia Tech at the time of this publication, where his research focused on operating systems and security. And he currently works at a company called Igalia, which is an open source consultancy service. And he earned his PhD from Saskatchewan University. And lastly, Tae-So Kim is a professor of computer science at Georgia Tech. His research focuses on fuzzing, operating systems, and system security, and he earned his PhD from MIT. So now that we know the background of the authors, the first question that you might have is, what exactly is fuzzing, and how does it work? So software fuzzing is a technique to find bugs and vulnerabilities in programs, and it works by repeatedly mutating inputs to try and find bugs. So in the diagram on the left, the random inputs are presented as binary, but the structure can range from anything from structured to unstructured inputs of different kinds, like JSON or just random hex sequences or anything like that. And it varies based on the software that's being tested. And the software that's being tested can range from really simple programs to entire libraries, such as those tested by libfuzzer, which I'll get into later in the presentation. And this paper focuses specifically on some coverage-guided fuzzers, such as AFL, which AFL is presented on the right here, so you can see what the screen looks like when you run it. And coverage-guided fuzzers record when inputs hit new, quote, untouched parts of the program and record those seeds as interesting, and then they get added back into the seed pool for further mutations. So these kinds of software fuzzers also record crashes to determine when inputs broke the program during execution so that they can be recorded for future analysis. And AFL is a popular fuzzer, which is shown in the image on the right, and it uses coverage-guided fuzzing to find bugs and crashes. And to produce new input, it uses a variety of bit and byte flips, trimming, arithmetic operations, etc. You can see some of the techniques that they use in the bottom left corner of the AFL screenshot. And this seems great and all, but to understand the importance of this specific paper, we have to know how fuzzing actually works under the hood. So how does fuzzing work? So this slide demonstrates a simplified fuzzing structure based on AFL. So AFL makes use of a fork server to coordinate different instances of fuzzing runs. Basically, the fork server creates new trials that are in a ready-to-run state in new processes. And these processes then get input from AFL's mutation engine. And each of these separate processes record their own bitmaps based on what edges each test run hit. So these bitmaps are independent for each of the processes, but they are periodically synced to the shared memory. And this updated shared memory and the associated seeds that are then selected for mutation are then refed back into fuzzing instances as inputs. So basically, good inputs are saved again and fed back so that they can be run and mutated on more often. So what may be some problems with this approach? So currently, most research has just been on how to better improve the mutations. And this is because better mutations are assumed to lead to better coverage, which helps better explore the program and give the user more of a chance to find bugs. And the authors of this paper focused on some areas such as the repeated use of the fork call and the synchronization of shared memory by many processes. And then they also looked at the effect of the file system on repeated fork calls. So the authors were a lot more worried about the speed of the system doing certain actions compared to improving the mutation technique. So now that we have covered the general background of fuzzing, what does this paper cover? So this paper attempts to solve the problem of bottlenecking fuzzers. So prior to the publication of this paper, computers with 16 to 64 cores did not really scale well with fuzzing. And these bottlenecks in these high-powered systems just lead to many wasted CPU cycles from contention in the operating system. And several inefficiencies have been identified by the authors of this paper. And the first was the use of the fork system call. So this creates new processes that each run a fuzzing instance. And these calls include unnecessary operations such as an update of the reverse mapping of the physical page. And these calls also stress the global memory allocator. And the second inefficiency is the creation of the test cases. So each independent fuzzing instance saves its own system metadata and relies heavily on calls to the open and create system calls to generate test cases, write or for flushing interesting seeds and reading for loading test cases. And all of these calls creates a lot of file contention with all the repeated usages. And lastly, this paper identified memory synchronization as a potential problem point. And as the previous slide showed, each process needs to sync their memory to record all of the, quote, interesting seeds found. And initially, this approach involved iterating through test case directories of other fuzzing instances, determine if the test case had been synced, and lastly, execute the test case to get its bitmap to see if it was actually useful. And this is really computationally draining as the number of test cases to scan increases exponentially compared to the number of fuzzers, or the number of fuzzing instances. So now on to the actual implementation to solve these problems. So the first problem that we will look at is the fork system call. So how to run each instance efficiently. So as shown earlier, current fuzzers operate by using the fork servers to run a series of new processes executing on the target with new input. So this is shown under the structure header on the right, where AFL has different AFL apps that each have their own private directories. And each of these apps operate as separate instances which are created using the fork system call. So each of these executions of fork system call is inefficient for the operating system since many things get updated, such as the reverse mapping of the child's physical pages, which are used for swapping. These have no real effect on the specific instances of the targets executing with AFL, so less overhead can be done and still provide the same services. And this again was the approach taken to speed up each execution of the fuzzing processes in order to give the fuzzer overall better odds at finding a new bug. So to make this process more efficient with the new process creation, the authors of this paper created the snapshot system call in the Linux kernel. So this call works by the target process sharing the user space execution context, which is just all the current registers and signal maps. And then the first step is that the system goes into the waiting on block loop and waits for new fuzzing requests as shown in step number 1 in the diagram. And when a request occurs, a call to snapshot is made to reserve kernel context and registers the callback function as shown in step number 2. In step number 3, the actual instance of the fuzzer is run with the main function until it is exited, returned, or killed. So once any of these 3 actions are done, it enters step number 4. And this is the epilogue to return to the previous state after the fuzzer is done executing in that instance. So this is done with the callback function. So to put this in simpler terms, the snapshot function just saves the general context of the fuzzer before the individual instances are started with different test inputs. And once each of these instances run, then the snapshot function restores the context from before the instances were run. So to make this function work, several changes were made in the kernel, and these changes included updates to the VMA or virtual memory area in the page table system. And this system maintains a set of pages that belong to writable VMA and use a copy on write technique to keep original memory status. And it does not change permission of mapped writable virtual addresses, which the kernel has not allocated to physical pages. So all of these changes were about 700 new lines within the Linux kernel to get this feature working. So next, on to problem number 2. So the problem of executing test cases again. So the next problem that this paper focused on was how to improve memory synchronization. Specifically, when different fuzzing instances find new results that are interesting, how do we best share this with other instances of the fuzzer running? This is important since if we share the interesting test cases between all the other fuzzers, this allows them to have more of a chance of mutating on previously effective inputs. This is better for fuzzing since it allows the fuzzer instances to learn more from each other and learn more efficiently. In the current approach, when interesting test cases are shared between different instances of fuzzers, the test cases have to be rerun. This is very slow since it involves the interesting cases being rerun many times to generate the bitmaps for each of the individual fuzzing instances. The authors of this paper propose that there has to be a better way of synchronizing memory between all the fuzzing instances. So their solution was the shared in-memory log. So these changes were done with a master test case log that can be accessed by other fuzzing instances as a slave. And this test case log is a circular queue that only the master can add to, and each slave has its own tail marker as the test cases are, quote, synced to each fuzzing instances. So to add new interesting test cases, a fuzzer can push the test case so that the queue contains the file name and the bitmap for that test case. And when all the fuzzing instances have used the interesting inputs to update their individual bitmaps, the tail marker of the circular queue is moved forward. So the diagram on the left displays this functionality. The queue stores general information about the inputs, such as the test case, file name, metadata, and the bitmap, which shows parts of the instrumented program that this specific seed hit. By doing this, there is no need for multiple instances to re-execute test cases to get their bitmap information, since it is efficiently shared in the queue. Therefore, this solution lowers the synchronization time so that the fuzzer can spend a greater portion of the time executing new inputs compared to just synchronizing like before. And this change was made outside the Linux kernel, unlike the snapshot system call. So this affects the fuzzers directly, so it had to be integrated into AFL and libfuzzer, which were the 2 fuzzers that this paper tested. And lastly, the final change that was addressed from the final problem was system and file congestion. So file system congestion. So how does file system contention occur? In high-powered machines like those being used with up to 120 cores in this experiment, many files are being created and closed all the time for each test case running. As the number of fuzzing instances increase, the number of total fuzzing test cases increases exponentially, since each fuzzer will test hundreds to thousands of tests a second. File system contention mostly affects the highlighted area from above, or in the diagram, specifically with the creation of new fuzzing instances and the storage of bitmaps. How might this system be improved so that the file system is not being clobbered by too many system calls within the same directories? So, to overcome the challenge of file system contention, the authors introduced the dual file system. This approach creates a private working directory for each instance of the fuzzer to avoid contention for accessing test cases and allows them to have their own independent file systems. This is done in addition to having a file system service that periodically checks whether memory usage is going above a set threshold. If this is the case, test cases are moved into the disk file system and they are replaced with symbolic links to the corresponding locations in the disk. This is done in an age-based model since earlier test cases are likely to have lower coverage and are less likely to be reread. So this change involved several hundred lines of additional code to the fuzzers directly as this was done outside of the Linux kernel. And for the results, when gathering the results for this experiment, the authors expanded the impact of the snapshot system call. The authors examined the impact of the snapshot system call, shared test case log, and the dual file system on the execution speeds of high-powered machines running fuzzers. Their hypothesis was that these changes would provide significant boosts to execution speeds as well as the number of cores on the machines increase. So here we can see the increased fuzzing efficiency. So this slide shows the results of the changes made on AFL specifically. So AFL benefited from the combination of changes with the dual memory system, the snapshot system call, and the shared test case log. So to test this implementation, an 8-socket 120-core machine with Intel Xeon and the E7-8870V2 processors was used. The library chosen to test were Google's Fuzzer test suite. So both ANL and libfuzzer were tested, but an additional wrapper was made to test AFL with libraries, whereas libfuzzer was already built to take in libraries as input. So these diagrams show that the optimized version of AFL performs significantly better as the number of processor cores scales. Some interesting results from this area are seen in the bottom center with OpenSSL. Fuzzing this with base AFL actually ceases to function after 90 cores due to the severe performance bottleneck, and this bottleneck does not appear in the optimized version. These bottlenecks do appear in the optimized version of AFL, but they appear with significantly more cores in the 60 plus range for libraries like libbong, C areas, and boring SSL. And libfuzzer showed similar results with better scaling, specifically for libpng and boring SSL compared to the base version of libfuzzer. And then these graphs on this page show more of the inner workings of AFL with the changes. So in the top left, you can see the performance of AFL with and without the in-memory test case log. The blue line requires more superfluous executions of test cases and more intensive synchronization, which reduce the total number of executions per second. And the bottom left figure shows that with the shared memory log, the amount of time synchronizing test cases does not rise above 8.05%, compared to around 90% with 120 cores without using the shared in-memory test case log. And the snapshot system call in the top right graph provides benefits up to a point. The peak around 60 cores is followed by a slight decline in the number of executions per second. And this is due to the continued high usage of the open and closed system calls, which became the new bottleneck once all of these previous changes were made. And lastly, the bottom right graph shows AFL's efficiency running libpng libraries with fork compared to snapshot by measuring the number of processes created. As you can see, snapshot can produce far more than fork as it scales with the number of cores. And eventually, it does take a significant drop after 60 cores for the fork system call. So for the discussion. In summary, This paper introduced a new way of improving efficiency in fuzzing. Fuzzing is a technique of random testing that involves high throughput of data into test programs, so increased performance comes with either more test cases being executed or better mutations. This paper used three methods: improving on the fork system call with snapshot, the dual file system, and the shared in-memory test case log to create a more efficient fuzzer. At least some of these changes apply to almost all major fuzzers available today, as they have similar base structure and make use of many of the same system calls and resources. This work showed that these changes were beneficial and greatly improved performance on high-powered computers compared to the base models of AFL and libfuzzer, but there is still work in this area that can be done. Some areas of future research include applicable fuzzers, cross-platform implementation, and fuzzing on VM clusters. Fuzzers that diverge from the standard models of AFL and libfuzzer will also have less benefit from these changes. For example, fuzzers that use symbolic execution, instruction emulation, or taint analysis will not benefit. Cross-platform implementation would help, as the majority of applications today are made for macOS and Windows due to their popularity. This experiment was done on Linux, but it would likely benefit more users on those other platforms. Lastly, VM setups will likely have different bottlenecks than regular machines due to the semantic gap between the VM and the hypervisor. And this would involve needing different primitives to interact between those entities to ensure that the performance benefits that are found in this system between the fuzzer and the OS would also be present between the fuzzer and the VM. And with the proposed primitives, AFL experienced a 7.7 times, 25.9 times, and 28.9 times improvement on 30, 60, and 120 cores, while libfuzzer saw speeds of 170.5 times, 134.9 times, and 735.7 times improvement on 30, 60, and 120 cores. And this just shows the benefit of these three changes. And from the perspective of someone who works with fuzzing, this paper was a nice foray into a unique way to increase fuzzer performance. Most research papers focus on how to better select seeds, either through random or custom structured mutation, to test different programs. By focusing on the application to high-powered machines, the authors took a new approach with the use of system calls added to the Linux kernel and modifications to the fuzzers. My main gripe with this paper is that these changes are very difficult to implement in actuality. Many regular users are unlikely to manually edit their kernel or the distributions of AFL and libfuzzer, as these are massive programs with dozens of files and large repositories on GitHub. Past research focusing on seed mutation was more user-friendly, as users can easily tweak the mutation strategies, and many fuzzers are designed with that intention in mind. I would have also appreciated a more focused view on examining the effects of changes individually. It seemed like all three changes were lumped together for most of the results, but I would be interested to see if certain changes accounted for better improvements in different environments. Thank you again for listening to my presentation.